So I'm supposed to give an introduction to radio astronomy, and so without much further ado, let me start. And the point I wanted to start out was by sort of with this particular fact, which some of you may be already aware of, that celestial objects that we know actually emit all kinds of radiation. We are usually used to looking at the looking at the night sky, and we look at it with our eyes and we see the stars over there, and we imagine that that's all that celestial bodies emit, that they emit only light. But that's just our feeling because our eyes are sensitive to light waves. If we had sensors which were sensitive at other wavelengths, we would have realized that that these objects actually emit all kinds of waves. And over the last century or so, it has become sort of very clear that celestial objects, in fact, are quite bright, not just in light waves. They're bright in radio waves, they're bright in X-rays, in gamma rays, and so on. The optical emission that we see comes typically from the stars, whereas the radio waves typically come from diffuse material, and that's what I'm showing you over here in this overlay. So if you look at the white stuff in this picture, it's a picture of two galaxies. There's a spiral galaxy over here, which is interacting with a companion over there. And the white stuff actually shows you where the stars are. Whereas if you look at it with a radio telescope and you ask where is the diffuse atomic gas in this particular situation, that's what's shown in blue. And you can see that the distributions have some overlap. They are not completely disjoint from one another. But at the same time, they aren't exactly the same. The distribution of the gas is quite different from that of the stars. If you look at the gas, you can see this huge tiny tail coming out over here, which you don't see in the starlight at all, right? So this sort of looking at it from the radio and the optical wavelengths has actually given you complementary pieces of information. Right? And so that's one of the main reasons why one does radio astronomy. I should just point out, and I'll come back to it later in the talk, that here I'm showing you radio emission which comes from diffuse gas, but there are other objects also which emit radio waves. In particular, there are compact objects, pulsars, which emit coherent kind of radio waves, which we'll talk about later in this talk. So this is the fundamental reason why one does radio astronomy, because it gives us a complementary view of the night sky. Right? And so like in this famous parable, if you actually want to understand the celestial object in its entirety, you do need to look at it from different aspects. If you were only to look at one particular point, like for example, if you were doing optical astronomy only, then that's all you see, and you think, maybe the elephant is like I don't know what they said over here, like a spear or whatever it is. You need to actually look at it in its entirety, and then you realize it's an elephant and it's not a sphere. So having said that, then what is so special about radio astronomy? You would imagine that what you need to do is that you need to look at things in the light waves, in the radio waves, in the X-rays, in the gamma rays, and so on. And that is in fact by and large true. But nonetheless, there is a special place for both optical and radio astronomy. And that special place is because of where we live in. We live on the surface of the Earth under an atmosphere, and the atmosphere actually is opaque to almost all electromagnetic radiation. So that's what's being shown on this graph over here. It's showing you the opacity, which means this is the height above the Earth at which the waves which are coming from outer space are absorbed. So over here, if it's at this height, these wavelengths are 100% absorbed. So none of it reaches the Earth. So if you want to observe anything on the surface of the Earth, you have to look for these windows where the radio or whatever wave you're looking at actually penetrates to deep down through the atmosphere and can be observed on the surface of the Earth. And you can see there are really only two major windows. There's one more in the near infrared, which is not highlighted here. So this one is the optical window, which goes, as you know, from blue to red. And this is the radio window, which goes from wavelengths of a few tens of meters to wavelengths of the order of a few millimeters.
Can you just use the mic?
Really? Okay. Let's see how this works. Got it? Note. All right. maybe just that I was speaking too fast. I find it hard to believe that my voice was too soft. But but I'm glad you stopped me, and do stop me in between because I'm going to rattle on and I'm going to cover a lot of ground. So if you have any questions, just stop me. All right. So this is what we were talking about. There are basically two windows at which the electromagnetic waves reach the surface of the Earth. One of which is the optical window, and the other of which is the radio window. And the same information is what's being shown over here. This is the same plot that we had, and it's sort of telling you what would happen if you wanted to observe at these wavelengths. So for example, supposing I wanted to observe at these wavelengths, which would be the far ultraviolet and the X-ray wavelengths, the only way to do that is to launch a satellite into space. You can't do it from the ground. And so of course it's very, very expensive to launch satellites into space. And you can't build very big telescopes and launch them into space. So this whole operation then becomes much more expensive. It's much easier and cheaper to build telescopes on the ground. And so that you can actually only do. So I suspect it was better. So that you can only do. I'll just try and speak louder. So that you can only do at optical and radio wavelengths. And again, just as a piece of information, I thought I would tell you that if you look at this radio window, it is sort of cut off at the short wavelength end and the long wavelength end. This long wavelength cutoff comes off because of the plasma in the ionosphere. The plasma in the ionosphere is actually opaque to long wavelength radio waves, and so it acts like a mirror. If there was a radio wave coming from outer space at those long wavelengths, it bounces off and it goes back into outer space. And that is a fact which has been used also in terrestrial communication. So, some of the older people, actually, probably all of you too young to remember, there's something called shortwave radio, which is not really that short a wave. It's actually waves of that order. So those things, for example, you could have a shortwave radio station in London and you could pick it up in Pune. And how does that happen? Because there's no line of sight between these two places. It happened because that radio wave bounced off the ionosphere and came back, and you could receive it in Pune. So anyway, this bit of opacity, comes because of the plasma in the ionosphere. And over here it begins to cut off because they are absorbed by molecules in the upper atmosphere, molecules such as OH. And I'll say something again about OH towards the end of my talk. Okay, the other thing I wanted to emphasize over here is if you just look at the width of these windows, the optical window is actually quite narrow. It extends only about a factor of 2 in wavelength when you go from blue to red. Whereas the radio window is almost a factor of 10 to the 4 in wavelength, right? 10,000. So the short wavelength end is about 10,000 times smaller than the long wavelength end. And so because of this, the radio telescopes that you see are very, very different in their appearance, whereas all of the optical telescopes look more or less the same. At least if you were to just look at them, there will be fine details in the way in which they differ from one another. But in the radio telescopes, that's not the case. And let me show you now a zoo of radio telescopes. So this is a radio telescope which works at very short wavelengths, and it looks a little bit like an optical telescope. There's a mirror, a primary mirror, there's a secondary mirror over there, and it comes down to probably to a focus inside where you would have some instrumentation behind the dish. And the whole thing you have to protect inside a dome which rotates, and it has a shutter which opens so that you can see the sky. So that, in zero thought is very similar to an optical telescope. If you look at medium wavelength, which is a telescope like the GMRT, which is about 80 kilometers away from here, this is what it looks like. You can hardly see the reflecting surface anymore, right? All you see is this sort of these ribs which are supporting the reflecting surface. The reflecting surface is actually a mesh. And that's because the wavelengths you are operating at are all longer than about 20 centimeters. So any holes in this mirror which are small compared to 20 centimeters make no difference. There's no point in building a solid surface. It's just expensive. It'll have a lot of wind load, then you need a lot of backup structure to support that wind load. It's unneeded. So instead what you do is you just make a mesh and you put a mesh over there. Right? And, but again, it's a parabolic mirror. The light waves strike off the parabolic mirror, and this is a prime focus mirror. So it goes and it comes to the focus over there, and there's some instrumentation over there which receives the radio waves. Okay. And the last radio telescope I want to point out over here is something called LOFA in the Netherlands, and it doesn't look much like a telescope to you, right? It just looks like some poles sitting in the field. What you won't be able to see is that there are actually wires coming out from this pole. There's a wire like this and there's a wire like that. right? And those wires are antennas, right? And all of these antennas have been combined together electronically to make a radio telescope. So when you have very long wavelengths, this is the kind of radio telescope that you end up with. So you can see that it's actually quite a zoo of things which people call radio telescopes. All right, so let me just say something about the fundamentals of telescopes. Two reasons why one uses telescopes. One of them is that they're useful in order to detect faint objects. That's simply because the telescope acts like some kind of giant light bucket. It collects a lot of photons, right? So the bigger the bucket, the more photons you collect. Bigger telescopes collect more light, so that's a good thing. A good reason to build bigger telescopes. And the other thing is that a bigger telescope actually sees finer details in the object. And this is something you probably would have seen when you study diffraction of light, that the resolution that you would get goes like lambda over t. Some of you might have run into the AV disk and things like that, right? And the scaling that you have over there is lambda by t. So the shorter the wavelength and the larger the diameter of the telescope, the better the resolution. The more you are able to see fine details. Now, if you had, we just apply this formula to an optical telescope, and you take an optical telescope which is about 10 centimeters in diameter, you'll end up getting a resolution of about 1 arcsecond if you just did that thing. And interestingly enough, even if you take a large optical telescope and put it on the surface of the Earth and look up, even if you were to take a 10-meter telescope, the resolution you end up getting with is still 1 arcsecond. And why is that?
Lambda is high for radio.
No, I'm saying optical telescope. I think even a 10-meter optical telescope.
Because of Earth's atmosphere, the star is not stationary.
Yeah, there's turbulence in the atmosphere, and the turbulence in the atmosphere distorts the image. On very short time scales, the star jitters around, and so any reasonable exposure will end up in a blurred image. And that blurring is of the order of an arcsecond. But anyway, so unless you do something fancy, and people do fancy things these days, but unless you do something fancy, the typical resolution that you get in optical observations is of the order of arcseconds. So the world's largest radio telescope, there's something slightly larger coming online at the moment, but it's of the similar order. The largest telescope that one has, which is about 300 meters in diameter, right? And so this is a picture of that telescope. It's Arecibo in Puerto Rico. And so the reflecting surface is actually fixed on the ground. It's a spherical surface. And there's some optics over here which corrects for the spherical aberration and gets you things into a point focus. So anyway, if you use this radio telescope at a wavelength of about 20 centimeters, which is typical for that telescope, and you ask it, plugged in this formula again and ask the question, what's the resolution? The resolution is about 10 arc minutes, right? Which is much, much worse than 1 arcsecond. And to just pictorially give you an idea of how much worse it is, I just took a picture of the moon. This is a picture of the moon, showing you all these craters and these seas and all that stuff. And I just smoothed it down to a resolution of a few arc minutes. Right? So this is that image which is smoothed to a few arc minute resolution. It's the same image. I've just taken this and smoothed it to a few arc minute resolution. And you can see you basically lost almost all the information that this image contains. At most, you can sort of make out that this bit is a bit brighter than the rest of it, and it's a bit darker towards the center, but that's about all. Right? So this is what you would get if I were to try and compare a radio image at 10 arc minute resolution with an image at 1 arcsecond resolution. It's very, very hard to actually do any detailed comparison. So then that whole story that we were building up, that if I wanted to understand an object, I have to look at it at multiple wavelengths and then put all of these things together, that pretty much goes out of the window, because on one wavelength gives me so much information, the other one just tells me that it's a sphere and it's a little bit bright on one side, so not much you can do with it. So what you would ideally like would be to make a radio image which had the same resolution as this, right? Which had a resolution of 1 arcsecond. So let's see what you need to do that, right? So it's just to summarize, we have optical telescopes which have an angular resolution of about 1 arcsecond, which is set by the turbulence in the atmosphere. And if I just plug that lambda over d formula and I ask the question, what kind of d do I need to get a radio telescope with 1 arcsecond resolution? You need a radio telescope which is 200 kilometers in size. And to give you an idea of what that is, I've just superimposed 200 kilometers on a map of Maharashtra, right? So that is Bombay, and here is somewhere here would be Pune. You can see that it's It's completely crazy, right? The idea of actually covering this entire area with some metal mesh or something, and then building some receiver, taking things to a focus. The focus itself would be high up and all that. It's just madness. So there's no way you can do this. You can't build a mirror which at radio wavelengths would give you a 1 arc-second resolution. So you have to do something different. And the thing different that you do is interferometry. And so let me just start with this picture, which is very similar to the Young's double slit experiment that you might have seen. Now what you do is, instead of building one big radio telescope, you build 2 small radio telescopes, but you separate them. You don't put them right next to one another, right? You put them some distance L apart. And now we look at what happens to waves which are coming, let's say, along the axis, and waves which are coming along some angle theta. So you can see for waves which come along, come vertically, the wavefront is perpendicular to the separation between the antennas, and so it reaches both these telescopes at the same time. They would be in phase, right? Whereas the thing which is coming at this angle, it reaches this telescope first, and then it has to travel that extra distance to reach the other telescope, right? So the other telescope, there would be, the wave when it reaches it is lagged, and so there would be a phase difference between the two. So if I were to add up the voltages, add up the signals which come from these 2 telescopes, if I was looking at something vertically upwards, things would add up in phase. I would get a large signal. And if I were to look at it, if the thing was at an angle, it would not add up in phase. And in fact, if the angle was such that the phase difference was pi, it would exactly cancel out, right? I would get no signal. So it actually allows me to distinguish between things which are, distinguish between the position on the sky, right? And when I need a phase difference of pi, I need, a cancellation which would happen when theta is equal to lambda by 2L, right? When this extra distance that it has to travel is lambda by 2. And then it would be out of phase, and that means that the angle that I can see would go lambda by 2L. So it's very similar to the formula we saw before, where the resolution was lambda by d, excepting the thing which comes in the denominator over here is not the diameter of the telescope, but the separation between the 2 antennas, right? So you can actually get information on scales which correspond to the separation of these 2 antennas. Of course, you don't get the sensitivity. You don't collect, if I had a mirror which was this big, it would collect much more energy from the radio wave. Here I'm not. I'm only collecting the energy which strikes this mirror and that mirror. So I haven't improved my sensitivity, but I have improved my resolution. Yeah.
Sir, if this length must be somewhat of the order of lambda or greater, right? So, the length between the 2 telescopes. So, what about the coherence of the 2 incoming waves? So, for that larger length, will those 2 waves be coherent with each other?
What do you mean by coherence?
I mean, for Young's double slit experiment, the 2 waves which interfere with each other, they must have a constant phase relationship, because they have to be coherent for them.
Yes.
So, will these 2 be coherent because they are the D is very large?
Yeah. So the coherence doesn't have to do, the coherence is an inherent property of the source, right? You had put in the Young's double slit experiment, you put a coherent source, right? So it doesn't have to do, in some ways the properties of the source may map onto properties over here, but it's fundamentally, we are asking the question whether the wave falling on this thing is coherent at the 2 antennas, right? And when you did the Young's double slit experiment, you all would have, do you remember what source you used?
You used a sodium vapor lamp.
Why was it a sodium vapor lamp? Do you remember? Did you? Sorry?
Monochromatic.
Because it was monochromatic. And a monochromatic source is coherent,
Yes.
right? So that is the thing, that we need a source whose properties are such that things would be coherent over here. We won't work with monochromatic sources, because monochromatics, I'm not going to go into it now, but if we were to look at things only at one wavelength, we don't build a very sensitive device. So we want to look at it at large wavelengths. But what we will require is that the bandwidth that we look at, the delta lambda that we look at, is small compared to the lambda. As long as that delta lambda is small compared to the lambda, then things are coherent. Okay, So anyway, to come back, you're right, I have to assume that there's coherence of the wavefront between here and here, and that delta lambda by lambda we ensure by actually building filters into our instrument. With you could have, you used a sodium vapor lamp, but you could also have used an ordinary lamp and just put a filter in front of it, which allowed only a certain wavelength through. So that's what you do over here. So we can look at any source in the sky because we put that filter in front, which makes the delta lambda small compared to the lambda. So if you were to take these two antennas separated by a distance L and we were to add the signals from them, we would actually get this some information about the position of the source, and that information would be on resolutions which would go by lambda by L. Of course, this doesn't allow us to build an image, right? It gives us some information on the position of the source, assuming that the source is a point source. But ideally, what you want to do is you want to image the sky. So what one does in order to image the sky is that you have to do a slightly more complicated operation, and I'll just tell you what the operation is. We won't go into the details of why it works. Like you take the signal from this antenna, you take the signal from that antenna, you multiply them together instead of adding them. You multiply them together and then you just average it for some time. And it turns out that when you do this operation, you will actually get the output that you get over here can be used to image the source. And I'm going to explain that in two ways. One is for people who have done Fourier transforms, and since many of you may not have, I'll just sort of say it in other words again later. So for those of you who have done Fourier transforms, it turns out that what we do measure when we do this, it's called a correlation when we multiply and integrate. This correlation interferometer, it measures one component of the Fourier transform of the image, right? And it's the component which corresponds to the frequency B over lambda, where B is the separation between the two antennas. And so this is under a number of simplifying assumptions that this statement of ours would hold true. And the assumptions are that the field of view is small, or that the measurements are all in a single plane, that the observation bandwidth is small compared to the central frequency, which was something we just now discussed, and that all the instrumentation and propagation effects have been properly calibrated up. But if all of these are true, then it turns out that what you measured is a single component of the Fourier transform of the image, and if you have enough interferometers, you can measure enough components of the Fourier transform. And you know that the Fourier transform is invertible, so you can invert it uniquely to get the image. So effectively, you're going to synthesize a telescope whose size is equal to the size of the array. It's no longer the size of each individual telescope. All right? And for those of you who haven't done Fourier transforms, I'm just going to say this in different words, but it's basically the same thing. That indirect image formation is possible if you correlate the signals instead of adding. If you add the signals, you can't do image formation, but if you correlate it, you can indeed form signals. You can indeed form an image. And each correlation, every time I take to an antenna pair and multiply the signals together, it actually gives me information on a specific angular scale of the source. And under suitable approximations, this information can be inverted to get the image back. And so basically the antenna pair is acting like a filter. It's acting like a spatial filter, and it's filtering out spatial components of the image. Wide pairs will pick out very fine details in the image, whereas close-by pairs will tell me something about the large-scale diffuse emission in the image. And so if I have all the pairs at all these separations, from very nearby pairs to very large pairs, I actually have information on all kinds of angular scales, and I can put it all together. And to do that, to do it with high fidelity, you need good sampling of all scales. You need both distant and close antenna pairs. So this is what people do in radio astronomy to get high angular resolution. There are various other tricks you could play to get good images. The first one is that the sources that we are looking at simply don't vary on human time scales. Most of them don't vary on time scales of years and maybe even hundreds of years. At least their statistical parameters don't, which is what we are interested in. So you could synthesize a large aperture with only two antennas at one extreme. If they were movable, I could put them at different separations and make these measurements. It might take me years to make these measurements, but I can put them all together because the source has stayed steady through all of this. Right? So for example, by mounting the antennas on tracks, I can do this and I can get an image. Or another way of doing to get better information on all scales is just to track the source as it rises and sets. That's because all of our antennas are on the surface of the Earth, and as the Earth rotates, the projected separation between the antennas also changes, right? And so effectively, the distance that you see, the lambda by b, the b in that is going to change as the antennas rise and set, because of the projection effects. And therefore, you would get a good coverage of the Fourier plane, which is also called the UV plane, without moving the antennas. I don't need to move the antennas. I just need to follow the source as it rises and sets. So let me just show you a few images. Here is a very, very early, these things are also called interferometers, which was used for imaging, and it had only two antennas. There was one over here which was fixed, and a smaller one here on an antenna which was on rails. You could move it in and out and measure different spacings with it. This is, I'm just showing you a cartoon to see what happens when the Earth rotates. So basically, as the Earth rotates, when you're looking at it from space, it's like this whole antenna array is rotating. And so if you put all of it together, you're going to get a much better coverage than you would if you just observed it for one instant of time. And you could use both of these. You could put your antennas on tracks and sort of follow the source as it rises and sets. And there are telescopes which do that. This is a very large array in New Mexico in USA. And so what it does is that it has these antennas, all of which are mounted on tracks. And these antennas themselves are, they are mounted in such a way that you can follow a source as it rises and sets. And you can also move the antennas in and out on those tracks, so you get coverage both by tracking the source and also by moving the antennas in and out. And I also mentioned, since the coverage that we're interested in is basically depends on lambda by d, it's always the ratio of lambda by d which decides what angular scale you're looking at. If I could have a range of filters, which pick out different lambdas each time, then I'm actually measuring different angular resolutions. So if I could measure over wide bandwidths with something like a spectrometer, which gave me a measurement for small delta nu at each nu, then I could also get a better coverage of the UV plane, and that's something we'll talk about in a minute. Okay, before I move on, I'm going to tell you about the GMRT, but I wanted to also say something about the way the radio telescope is set up. So typically the way it works is like this. We have some antenna which receives a radio wave. This radio wave, what the antenna does is it converts the radio wave, which is a wave in free space, an electromagnetic wave in free space, it converts it into a voltage. So it's like a transducer, right? It's like a microphone or anything. So a microphone does something similar, right? It takes an audio wave, it converts it into an electrical voltage, which is then amplified, and you do something with that. An antenna is like that. It's a transducer. There's a radio wave propagating in free space. This antenna couples to part of that radio wave, and it generates an electrical voltage. So once you have generated the voltage in here, it's a very, very weak, it's a very small voltage, it's a very faint signal. So the first thing you have to do is that you have to amplify it. So the first block that we will put over here is an amplifier, which I will call a low noise amplifier. And the reason for that is because any amplifier that you pick is going to generate noise that you would probably all of you would have noticed, right? That you put on your radio or TV or whatever. There's typically a hum and a hiss over there. That hiss has many, many components, but the dominant component over there in that hiss that you hear is the noise produced inside the amplifier. So any amplifier will not just amplify the input signal, it will also add noise. So it's very important when the signal is faint that the amount of noise that you add is very little. And so you need very special amplifiers over here, which are called low noise amplifiers, whose gain, they may not amplify very much, but the important point is that they will not add a whole lot of noise. Okay. So that's very critical. Once I've amplified the signal, then the signal's already quite strong. So if I add a bit of noise to it, it doesn't matter so much. But when the signal is weak, it's critically important you don't have noise. So these amplifiers are very special. Sometimes actually this entire piece of equipment would be cooled to cryogenic temperatures, again just to reduce the noise in the system. Because right at the start when the signal is weak, it's very important to amplify without much noise. So then once you have done that, you now have a stronger signal, which you could transport somewhere for processing. Because you remember these antennas are sitting out in a field somewhere. I need to bring them somewhere and bring the signal somewhere and process it. And very often you have to transport them tens of kilometers before you're able to process it. So this wave, which is now oscillating at this voltage inside over here in this wire, it will oscillate at the same frequency as this radio wave which fell on the antenna, which is the radio frequency. This oscillating voltage I now have to transport tens of kilometers. And you have to transport it in some cable or something. So that would have been the traditional thing, that you transport it in some cable. So now I have to move it in a cable tens of kilometers, and all cables are lossy. And it's possible to build cables which have very low loss, but they would typically have very low loss only at one frequency. At any other frequency, they would be very lossy. So you can build a very special cable which at this particular magic frequency will transport with very low loss. But then that would constrain you to observe only at that frequency, which is what you don't want to do. Right? You would like to observe at any frequency, and so what they do is that they build a piece of equipment which translates frequencies. So it's called a mixer. So it translates frequencies into what's called an intermediate frequency, and this is the frequency at which the cable operates correctly. Okay. So you transport the signal at this intermediate frequency, and now you want to put it into some piece of equipment which will process it in some way. And again, this piece of equipment typically works well at one frequency but not others. This is called a backend. Usually this piece of equipment is digital. And so, and it turns out that for digital equipment, it's easiest to build this equipment if the band of frequencies that you're interested in is as low as possible. If I wanted to observe, for example, a 10 megahertz band, I could observe, let's say, from 0 to 10 megahertz or from 110 to 120 megahertz. They're both 10 megahertz wide. But it's much harder to build a piece of equipment which works from 110 to 120 than 0 to 10. It's easiest when the frequencies that we're dealing with here are as low as possible. So it's a compressed band frequencies. I won't go into the details, but if you're interested, you can talk about it later. So usually what you do is you will put another mixer which moves the frequencies into frequencies which the backend works well at. So this would be the block diagram of a typical receiver, the radio telescope receiver. So the way the mixer works actually is very simple. What you do is that you have some incoming voltage which is oscillating at radio frequencies. You just multiply it with a sine wave which is oscillating at some other frequency which is called the local oscillator frequency. And you put it into some device which kind of does a multiplication of these two. So you're multiplying sine A, sine B, which means you're going to get sine A plus B and sine A minus B. You get the sum and difference frequencies. So you can actually move things around in frequency. You will filter out one of the two. I mean, supposing you're interested in sine A minus B, you filter out sine A plus 3. And so you get just one of them to proceed down. So that's what you do. This mixer is basically more like a multiplier. So this will be one local oscillator, there's another local oscillator, and you receive it over here. So all radio receivers work like this. So for example, even the FM radio that you listen to, you have only one speaker. Yeah, okay, go ahead.
So can you please repeat the last one?
Which way?
That how the mixer.
Oh, okay. So the mixer, as I said, is you can view it, very simply speaking, as a multiplier and a filter. So supposing this is the sine wave coming in from the sky, which is at radio frequencies. I generate and multiply another sine wave over here, and I have control over this frequency. I have a knob which allows me to change this frequency. And depending on which frequency I'm observing over here, I change this frequency so that let us say the difference is constant. Right? So I can observe any frequency I want by suitably adjusting this guy over here. Supposing I want the difference between these two frequencies to be 100 megahertz. I will, whatever sky frequency I want to observe, I just put this 100 megahertz below that, and I filter out only that piece. So I get, effectively I observe whatever I turn this knob to plus 100 megahertz. Right. So I was going to say, it might sound a bit, esoteric to you, but you guys do it all the time when you listen to any radio station, because you have only one speaker at the end. Regardless of which radio station you tuned into, all that signal is coming out at that speaker. And the different radio stations are at different frequencies, right? All of them tell you which frequency they are at. They tell you Radio Mirchi 109, 1 point whatever, or the other, and so on. They're telling you which frequency they are at in case you forget. So basically, these things are coming in at different frequencies. When you're tuning, you're just changing this guy's frequency. And so you finally get this 20 hertz to 20 kilohertz, which is the thing which you feed into your speaker and which you hear. Right? So so a radio telescope, in that sense, is really very similar to what you have in your own small radio receivers. The system is called super heterodyne. And I motivated it for you in a particular way by saying that this antenna was out in the field and we wanted to receive some signal many tens of kilometers away. And so we had to transport it in the cable. Then I had to change the frequencies again to get some frequency range with which the backend works correctly. Okay? So these days the picture is slightly different, but nonetheless you do generally have this need to translate frequencies around. And that's because most of this signal transport happens in the fiber optic, using fiber optic cables. And very often it also happens digitally. Okay? So what generally happens is that you have a digitizer over here, which digitizes the frequencies, and then sends a digital signal down to the back, which is then processed in some way. But even though the technology is slightly different than what I described, nonetheless, the broad picture is the same, that we will at some point or the other need to move frequencies around. Okay, so now I want to talk about the GMRT very quickly, and then I'll tell you something about what you do with radio telescopes. So this telescope, which I don't know whether you will be visiting at some point, probably yes, is located about 80 kilometers from here, and it consists of 30 antennas, each of which is 45 meters in diameter, and it's spread over an area of 25 kilometers in size. And I've shown you a picture of a few of the antennas in the central square. It's one of the most sensitive radio telescopes in the world at many of its frequencies of operation. So this is where it is, between Pune and Nasik, about 70 kilometers north of Pune, 160 kilometers east of Bombay. And if you look at the way the antennas are configured, this is the way it is, that there are 12 dishes in a compact array over here, and there are these rest of the telescopes are distributed in these roughly Y-shaped arms, each of which is 14 kilometers across. And so what this allows one to do, it's called a hybrid configuration, that the antenna pairs over here give you a number of pairs at very short spacing. So as I was describing, it gives you information on the large scale structure of the source. Whereas the antenna pairs produced by combining arm antennas will give you very wide separation pairs, and so they give you very high angular resolution. So with a single sort of observation, you can make images at a very wide range of resolutions. And I'm showing you again over here the same thing, that if you look at the coverage, what kind of sampling do you get? So this is the sampling of the entire telescope. If I were to track a source from rise to set, and that's 25 kilometers across on the side. If I were to zoom in on the central part and look at it on 1 kilometer on the side, the coverage is still pretty good, right? So even on scales of both 25 kilometers and 1 kilometer, you can get good coverage. And so it allows you to do things like this. So for example, I'm showing you acetaldehyde emission from the central part of our galaxy. This is an image of the acetaldehyde emission, which is these sort of contours over here, overlaid on a radio background of the continuum emission. So this stuff is telling you where the acetaldehyde is, this stuff is telling you where the total diffuse gas is. So if you were to look at it with the central square telescope, you can see this large-scale structure, right? You can see that there's actually quite a large cloud containing acetaldehyde molecules in the galactic center. If I were to make an image using the arm antennas, I just zoom in on this part, and then you see that it has a lot of fine-scale structure in it. The cloud is not homogeneous. And in fact, the structure that you see over here is tracing shocks in the cloud, which is understandable because the acetaldehyde molecule is supposed to be formed on dust particles and dust grains, and they stick to the surface of that dust grain, but in shocks they get sputtered out of the surface of the dust grain. They go into the gas cloud, and you can see it in emission. All right, so The GMRT, as it was built, actually had these 4 feeds which operated at these narrow wavelengths we were discussing a while ago, that you have to filter it and observe at narrow wavelengths in order to be able to make good images. And they were all mounted on a rotating turret. So depending on which frequency you want to do, you can rotate the structure around to bring the feed that you want to focus, and you can actually observe that particular frequency. And it supported a maximum bandwidth of 32 megahertz, and it supported 2 major modes of observation: correlation, which we spoke about for image formation, and beamforming for high-time resolution studies of compact objects, which I'll say something about in a minute. Right. And I'll skip this slide. It basically just tells you the way in which it operates. It operates in a way which is unbiased, which anybody in the world can submit proposals and get time on that telescope. And at the moment it's being upgraded, so almost everything is being changed except the steel and concrete. We're ending up with nearly seamless coverage from 30 to 1500 megahertz. The bandwidth is going from 32 megahertz to 400 megahertz. And all the other systems that you need to change along with that are being changed. So to just give you a pictorial view of it, we looked at it in frequency space from say about 100 megahertz to 1400 megahertz, which is the frequency in which the telescope operates. These blue lines show you where the old telescope operated, where the pink one shows you where the new one operates. So you can see that we are now operating on a much larger frequency range than we did earlier. There are pieces over here where we do not operate, and that is largely because there is a very hostile interference environment in these 2 bands. So over here you have digital TV, and over here you have cell phones. So the signals are so strong that they completely dominate the astrophysical signal, and you just have to filter them out. Okay, so what is it that people look at with radio astronomy? They look at all kinds of objects, and I've just listed a set over here. You look at the sun, you ask yourself questions like what heats the solar corona, how does the mass ejected from the sun travel through space and affect us on Earth? These are all things that radio astronomers study stellar evolution and end products. You look at supernovae, supernova remnants, pulsars, and pulsars themselves are of interest in themselves, and also as probes of the interstellar medium and fundamental physics. You study spectral lines from ionized gas, atomic gas, molecular gas, and again, questions you ask are of the sort: how does material cycle between gas and stars? There's a kind of the way in which you have oxygen cycles and water cycles on Earth. You actually have a cycle in galaxies between gas and stars, and how does that work in detail? What's the total dark matter content of galaxies? How does the gas content of galaxies and the intergalactic medium evolve with time? These are all things that radio astronomers study. You study also diffuse plasma between stars and galaxies. For example, a key question that people would like to answer is how did the universe get magnetized? We study active galactic nuclei, which are basically galaxies which host supermassive black holes. And again, a key question that people ask is what role do supermassive black holes play, for example, in the evolution of galaxies? So I'll just give you some examples from these, not a whole lot. So let me start with the pulsars, and in particular, let's look at millisecond pulsars. So pulsars are objects which have the mass of the sun with a radius of about 10 kilometers. They have densities similar to the density of atomic nuclei, and very, very intense magnetic fields of the order of 10 to the 10 to 10 to the 12 gauss, and coherent emission along the poles. Right? So coherent means like a laser, that all the particles which are emitting are emitting in phase, and that makes it very, very bright. And so key questions that you could ask is how do you produce such a dense object, right? An object which has got the mass of the sun, but its size is about the size of the city of Pune, right? You have such a small object, but it has got the mass of the sun. And it turns out you produce these during the death of massive stars, during core collapse at the end of massive stars. As stars, they burn up all of their internal fuel, hydrogen to helium, helium to carbon, and so on and so forth, to higher and higher elements. This process can continue and extract energy, nuclear energy out of this, only until you reach which element?
Iron.
Iron, right? Because iron is the most stable element. But once you have done that, you can't extract any energy any further out through nuclear burning. And so what is then going to happen is that the gravity will overwhelm the star and it is going to collapse. And it does so in such a dramatic fashion that there's actually a shock which gets driven into the star. The shock causes the inner part of it to contract down to nuclear densities, and it blows out to the outer parts of the star. So the outer parts get blown out into what's called a supernovae and a supernovae remnant, and the central part of it gets left behind in what's called a neutron star. because the material over there is predominantly neutrons. So then that's how you produce these. But how do you spin up such massive objects, right? How do you spin them up to millisecond periods? So milliseconds is like the period of your kitchen mixing. You've taken an object the mass of the sun, and you're spinning it at the rate at which a kitchen mix is spinning. So how do you do that? So the idea is that it's very interesting. This spin up actually happens when you have binary stars, right? So the bigger star explodes as a supernovae, like I just described, leaving a neutron star behind. And then this neutron star is very dense, it's very compact, and it has a very strong gravity, and so it gradually starts pulling material out from the companion star onto itself. And so as the material from the companion star falls onto it, it's basically what's going to happen is that the orbital angular momentum which that material has gets converted into spin angular momentum of this object. So this object spins faster and faster until you finally spin at millisecond periods. So I'm showing you that over here. Here's the first neutron star which was produced, which was spinning because the original star was spinning, but gradually it loses its energy and it slows down. But after a while, what happens is that this object begins to evolve and it begins to get a little bit bigger. And as you'll see in a moment, its outer parts begin to get tidally pulled and start falling onto the first object. And as it pulls, as I was saying, as it falls in over there, the orbital angular momentum of that object, the orbital angular momentum of the material which was falling in on the star, it's converted to spin angular momentum of the object. So this neutron star is now spinning faster and faster until finally it spins at millisecond wavelengths. At millisecond periods. All right. Let me move on. Let me talk to you about measuring the matter in the total mass content of galaxies. And let me, yeah.
So, when we are discussing about the binary stars, so we will observe the time period changing until the other binary star is getting merged.
Yeah. So maybe I went too fast through that. So, but one thing which I did not mention is that I did tell you there were coherent processes. So what happens is that basically particles get accelerated along the magnetic fields, and they come out along the magnetic poles. The radiation that we see comes out along the magnetic poles. And if the rotation axis and the magnetic axis are not aligned, then you see a picture like what is happening over here, right? That it's like a lighthouse. That there is this beam which is rotating in space, and every time the beam is pointing towards you, you see a pulse. So that's how you measure the rotation. Right, so ask me the question about the rotation.
So, so now, will there be a variation in this pulse when the other star, the companion star is getting up?
It will, indeed. It will vary. The period will vary for all kinds of reasons. It could be erratic, and so on. There could in fact be a time when that pulse is completely quenched. I don't have it here, because what is happening is that you've got all this material getting dumped onto the star, right? And so that could completely quench the radio emission for a while. So while that process is going on, this pulsar could fade out completely, and if the accretion is episodic, you might have times when you don't see anything because the accretion is too much. It has completely overwhelmed all of any emission. It's prevented any emission from coming out. And then there may be a period when that accretion has sort of reduced, and you see the pulsar again. So while it's going on, you could have these episodes where you see the pulsar for a while and you don't see it for a while, but every time you see it, it's actually a bit faster than last time. Yeah, so while this process is going on, you can't use it as a precision clock. But when it is over, then you can use it as a precision clock, simply because the same way like a gyroscope, right? I mean, it's a heavy spinning object. It's very difficult for you to change the rate of spin. The rate of spin will change gradually as the object loses energy. It's going to radiate out. It's radiating out. The radio pulse that you see is a small fraction of the energy it radiates. And because of that radiation, it will gradually slow down. But that can be exactly predicted. Years does it take to speed down? I don't remember exactly my expectation. I think it's of the order of a few hundreds of thousands of years. I could be wrong. Yeah. Or maybe of the order of 1 million years or so. It depends on how strong the magnetic field is. So you should ask the pulsar folk, which I am not. Probably so B.C. Joshi or somebody would be able to give you a more precise answer.
Yeah. So when during the end of this process, it emits X-rays or radio waves.
Yes.
So when, but then by the time it reaches Earth, it probably, the process must have been over. So when it is traveling through space and time, the radio waves, will it be damped by the other gravitational waves?
Damped. It won't be damped, but what gravitational waves do is that they change the fabric of space-time. No? So they change effectively the distance that this wave has to travel to reach you, right? And so it could change the time of arrival because it's changing the effective distance that this wave has to travel. Now there are many things which change the time of arrival of a pulse. For example, it has to propagate through interstellar space to reach you. And interstellar space is very close to being a vacuum, but it's not in fact a perfect vacuum. It contains a plasma. And there are the plasma effects which actually cause the wave to go slower. Right? So that could change the time of arrival of the wave. And there are other things also. For example, if it were in a binary, all these kind of things. Or maybe if the star is wobbling a little bit, it would change the time of arrival of the wave and so on. So the gravity wave will change the time of arrival, but you have to be able to distinguish that from all the other things which cause the time of arrival to change. And so one way of doing that is to look at a grid of pulsars and look for coherent changes in the time of arrival. Because you would expect that all of these other effects that we were talking about are specific to this particular line of sight, and therefore each pulsar has a slightly different behavior. But if I had a sufficiently dense grid of pulsars and they all did something coherently, then something large scale has happened to them.
So, sir, when this pulse travels through the plasma, so there will be some damping in that in the radiation, and also should we expect some absorption lines in the spectrum?
From the plasma.
Yeah, due to the plasma. So there would, I mean, if it is passing through some gas or something, so we can expect some absorption lines.
You would. From the plasma, you don't actually generally expect any sharp lines, but you do expect sharp lines from any neutral material which comes in. So if there was neutral atomic hydrogen, for example, you could have, in the radio which has a line in the radio, you could expect lines. You do get actually from some plasmas, from thermal plasmas, you could get recombination lines. And those also could get stimulated by this. There are certain other molecules which have lines which could either absorb or get stimulated by this emission.
So is this, I mean...
But those would be very small. I mean, you're using the pulsar as a probe. It won't actually change the time of arrival in any particular.
Chemical composition.
Yes, to try and understand the gas between you and the pulsar.
So,
yeah.
How the conversion between the orbital angular momentum and spin angular momentum is detected?
Because the pulsar spins it. And the only way for it to do that is because its material has...
spin angular momentum of both the binary stars.
But they are also orbiting, no? Yeah. And the orbital angular momentum is much larger than the spin angular momentum. Okay, so here basically what you're trying to do is you're trying to measure the mass of objects, and again that idea is very simple. So for example, if we applied it to the solar system and I want to measure the mass of the sun, how do you do it? Let's say we'll look at this orbit of some planet, and we'll assume that the mass is dominated by the mass of the sun, and we can ignore the mass of the planet. And so then we get, for a circular orbit, you would get this relationship that V square would go like GM by R. All of you would probably have seen this when you studied high school physics, where M is the mass of the sun. Okay? So if I could measure the circular velocity of the planet, and I know the distance between the planet and the sun, I can measure the mass of the sun. Right? Because that's the only unknown left in this equation, assuming that I know G. And some of you may have also seen Kepler's law, third law for planetary motion, which says that the mass goes like A, which is the semi-major axis of the ellipse cube, divided by the period square. Which basically, if I were to cast this relationship in terms of velocity and distance, it would tell me that the V is proportional to 1 over square root of R actually. This is 1 over square root of R. So the velocity, as you go further and further away, the velocity will decrease like the square root of the distance. If I had things which were going in orbit around the central mass. And so if you look at the orbital speeds of the planets, they in fact do follow that very nicely. So here's Mercury, plotting orbital speed versus distance from the sun. And this line over there is that 1 over square root of r relationship that I was talking about. So it fits very nicely, and from this you can actually measure the mass of the sun. So you try the same thing for galaxies. If I wanted to measure the mass of a galaxy, I find something which is orbiting around the galaxy, and from the orbital kinematics, I should be able to measure the mass. So what we typically use for the probe orbiting around the galaxy is hydrogen. So galaxies contain both stars and gas, and a major component of the gas is atomic hydrogen, and which, as I said a moment ago, it emits a radiospectral line. It turns out to be at a frequency of about 1420 megahertz, and measurements of the Doppler shift of that line would allow us to measure how fast that line is moving. Right? And if we measure how the gas velocity is changing with distance, we can actually measure the mass of the galaxy. So let's look at a typical galaxy. So you can't see it too clearly, I think, over here. We needed the room a little darker, but I hope you can make out that there's a thin disk of material over here and a central bulge over there. So the stars, there is this bulge which is not there in all galaxies, but is there in some spiral galaxies. But all of them would contain the material in a thin disk, right? And most of the stars, in fact, would be in the thin disk of the galaxies. And if we look at the way in which the density of the stars falls as I go from the center of the disk to the edge of the disk, it actually falls very rapidly. The stars are very tightly concentrated towards the center of the galaxy, and there's a decrease as you go out towards the edge. The density falls out exponentially. And so I could actually calculate what the rotation speed would be as a function of distance for an object of that sort. Right? If I have all the material in a disk whose density from the center to the edge is falling exponentially, then this is what it would look like. So this is the rotation velocity as a function of distance. And I want you to look at this dotted line. Let's ignore the solid line for a moment. What it does is it rises to a maximum, and then it begins to fall. And this other line, which I hope you can see, is telling you what the rotation velocity would have looked like if all of the mass had been concentrated in the center of the galaxy. That's just 1 over square root of r, right, which we had looked at before. And you can see at large enough distances, these two curves meet. Because if I'm far enough away from the center of the galaxy, the details of how the matter is distributed in it don't matter. As far as we are concerned, we can do a very good approximation, take it to be a point mass at the center of the galaxy. So if I go far enough away from the center of the galaxy, even though the material is extended and distributed in an exponential disk, I should see the velocities fall like 1 over square root of r. Because by that time, all the details of this exponential disk have got washed out. As far as I'm concerned, there's some object right at the center. All right. But what do you actually observe? This is what one sees. So these points with the error bars are what one actually observes when one looks at neutral hydrogen orbiting around some galaxy. Here I'm showing it to you for galaxy AGC 3198. This line over here shows you what I showed you earlier, that if all of the mass was contained in that exponential disk, it should have risen to this maximum, and then it should have started falling and gradually started becoming like 1 over square root of r. And it doesn't do that, right? It actually rises and then it stays flat. And there is no way to get a rotation curve like this unless you allow the matter distribution also to be extended. There's no centrally concentrated matter distribution which could do this, right? Because any centrally concentrated matter distribution would give you 1 over square root of r finally. It doesn't do that. So the only way you can get this is if there is some component of the galaxy which is much more diffuse than the stars that you are seeing. There's no other way to get this rotation curve. And people have looked for whatever this diffuse component could be. They've looked at it at a number of wavelengths and they've never ever detected it. And so therefore they conclude that it must be in some kind of matter which does not emit any electromagnetic waves. And so that is called dark matter. So the visible galaxy that you see, it turns out, is contains a very, very tiny fraction of the total mass of the galaxy. It's something of the order of 10-15% of the mass of the galaxy. The bulk of the mass of the galaxy is actually contained in this halo of material, which doesn't actually emit any radio waves, which is called dark matter. All right, a couple more things which I thought I'd run through. I'm talking about what radio astronomers do. One is to look at mergers of clusters of galaxies. So we've been sort of zooming out a little bit. We've looked at pulsars, which are very compact objects in our own galaxy. Then we looked at galaxies. Now we are looking at clusters of galaxies. So matter in the universe actually clustered on many scales. If you look at stars, many of you probably know that stars come in star clusters, often clusters containing hundreds of thousands of stars. Galaxies also, it turns out, are not randomly distributed in space. They are typically clustered into things called galaxy clusters, which contain thousands of galaxies. And these clusters themselves are not randomly distributed. They themselves are clustered together in space. And since they're close by, they can actually collide with one another and they can merge. And you get very spectacular effects when you have mergers of objects which are this big. So I'm showing you one over here, where the white over here is the optical image showing you where the galaxies are. The blue is showing you where the hot X-ray emitting gas, the galaxy cluster contains both gas and star and galaxies. And so there's a lot of material in hot X-ray emitting gas that's shown you in the blue. And the red and the pink are basically radio images made with the GMRT. And if you zoom in on this particular thing over here, you can see that it has this particular shape. And so what the explanation over here is that that there is an active galaxy at this end, which contains a supermassive black hole in which the material is accelerated to supersonic speed, to speeds close to the speed of light. So you have these very fast moving charged particles coming out of it. And they sort of collect in this region where they get re-energized because of this cluster shock over here. And this re-energizing because of the cluster shock over there causes them to emit radio waves, which you detect. So it turns out that these kind of features that you see in typically in merging galaxy clusters are extremely good at tracing where the shocks are, what is happening to the intercluster gas over there. Okay. The final thing I want to end with is now talking about things on a still bigger scale and asking ourselves a question: Do fundamental constants evolve? So, for examples in theories such as general relativity, the standard model of physics, etc., there are many parameters, and some of them which you have certainly run into would be the speed of light, the Planck's constant, Newton's constant, and so on and so forth. And the value of these parameters are fundamental constants. That is, you derive them from laboratory experiments. There's no underlying theory which tells you what that value should be. Right? You determine it from experiments. And typically, most of these theories would assume that these constants don't vary with time or space, that they're the same everywhere in the universe. So if you check for the constancy of these parameters, it's hence a check of the validity of your model. Right? You can ask yourself the question, do these parameters vary with time and space? And so one particular way which you can do it is by using radio lines. Radio lines of a particular molecule called OH, which I had mentioned right at the start of my talk, is being responsible for absorbing short wavelength radio waves in the Earth's atmosphere. But it also turns out that they have long wavelength spectral lines, at frequencies of the order of 1600 megahertz. And this spectral line, it has 4 spectral lines, of which 2 are very interesting. The one at 1720 megahertz and the one at 612 megahertz. And what's very interesting about it is the fact that in certain astrophysical conditions, these 2 are exact mirror images of each other. The 1720 line will, when it is an emission, as it is over here, the 1612 is an absorption, and vice versa. So if you added the 2 together, you should actually get noise. And so what that tells you is that these 2 spectral lines are actually arising in the same cloud of gas. If they were arising in different clouds of gas because of Doppler shifts, then you might get some velocity shifts between them. But the fact that they are perfect mirror images of each other means that they have to arise in the same cloud of gas. Right? Now, the exact frequency at which this line occurs and which this line occurs depends on the fundamental constants. So if the fundamental constants were different, a long time ago, then these lines would actually not cancel exactly because they would shift with respect to one another. Right? Because the shift, if I change the fundamental constant, this line, for example, would move this way and that line would move that way. And so the cancellation no longer happens perfectly. So you can ask yourself the question, does it cancel exactly? And if it does, it actually allows you to place constraints on how much these fundamental constants are varied. And so this is a slightly older constraint that we have. We have something a bit better than this by a factor of few. But the constraints that you can get by looking at these spectral lines is actually of the order of a part in a million, right? And it's a constraint on this particular set of fundamental constants, where Gp is something called the gyro-proton ratio. This is the fine structure constant, and this is the electron-to-proton mass ratio. And so that's a remarkable thing, right? That you can sit here on this on Earth with a radio telescope and you can measure to a few parts in a million what these fundamental constants were at a distance of 3 billion light years away from you. All right, so that's about all I wanted to say today. Thank you for your attention. We've had a few questions, but I'm happy to take a few more. Yeah.
One basic question is that in the beginning we were comparing optical telescopes and radio telescopes.
Yeah.
But then if we need to do work a lot more on the radio telescopes to get a clear image as good as an optical telescope or even better.
Yeah.
Because if we do it the same as optical, we get a blurred image.
Yes.
So what is the exact purpose of the radio telescope when you are getting clear images using optical telescopes itself?
Because they trace completely different objects. The optical telescopes typically trace starlight. The radio telescopes are tracing gas or compact objects or whatever it is. So you're getting information on completely different parts of the object that you're looking at. Each one of you is giving you a kind of blinkered view of the object. If you put it all together, then you begin to understand the thing in detail, in its entirety. Yes.
So if some noise from the space is below the data, so we can't detect it. Like we can remove assume 2 meters per distance.
Yes.
To antenna.
Yes.
So they have particular limit of delta lambda, below which you can't take measurements. It will lose their coherent property.
Yes.
So that noise can't be removed from the observation.
No, these are two different things. One of which is under our control and one of which is not under our control. The delta lambda is completely within our control. It depends on the filter that we put in front. And typically what one does is one puts multiple filters. I might observe a very large wavelength, but I actually break it up into many, many small pieces, such that for each piece, delta lambda by lambda is small. That's completely under my control. It depends really only on the kind of instrumentation that we put. What you may not have control about, you have some control also about the amount of noise your instrument produces. Right? So maybe you might be able to control it in some way. Of course, it's very expensive. It depends also on how much money you have. Right? So if I have enough money, I can break it up into many, many pieces. I can have very, very small delta lambda. If I don't have that much money, I might not be able to do it at all. Right? But apart from that limitation, certain amounts of that is within our control. What is not within our control is the noise which comes from the environment. That noise is not within our control. There may be things which you can do about it.
Exposure time, like we can increase the exposure time so that.
Yes, so you can. All right. So yes, you can. So it would be good. I think maybe many of these questions will get clearer as you go along. But let me just answer that question again. Supposing there was nothing systematic happening to my data. Right? Then, as I increase the exposure time, the things would average out. It get less and less noisy, and I would actually get a better and better, a more deeper and deeper and sensitive image. But supposing there was something systematic happening to my data, for example, there was some external source of noise which is completely overwhelming my signal, then no matter how long I integrate, I can't do anything. My signal is already overwhelmed.
So,
Yeah.
in the pulsars, when they rotate, they emit radio waves.
Yeah.
So, what is the physical process responsible for that?
Okay. So that is actually a very deep question, which